One disadvantage of the Laplacian eigenmap algorithm is that it gives you values for the embedding only for the nodes or for the samples that you've used during training. So there's no obvious way or no easy way to infer locations in feature space for new data points that you might add. And that's something that locality preserving projections are able to do. So they are closely related to the Laplacian eigenmaps, but they do it in a slightly different way, in that the eigenvectors are not chosen completely freely, but they are constrained to be a linear combination of data points. So the xi are your data points. Z is a vector to be learned, so that's now the parameterization. And the eigenvectors, the components of the eigenvectors, so the alpha eigenvector, the ith component of the alpha eigenvector, results from the inner product between the data vectors, which are fixed, and some vector to be learned. And then if you later go and you want to calculate the embedding, which is this u here, for a new data vector, you simply put in a new x, and that sort of helps you calculating the feature for new vectors. So notice that this is linear, so therefore the name locality preserving projections. No, sorry. It's linear LPP, therefore the name linear LPP. So linear, and we will later talk about the nonlinear version of that. So this is the component version, and if you write it in matrix notation, it looks like this. So this is your vector that optimizes the mapping. This is a data matrix, and this is the parameter vector that you want to optimize. Okay, so this is your original optimization problem. You want to minimize this, and with this definition you plug in x times z for u. That gives you this one here, and you simply combine x, L, x transpose as a new matrix L dash, and then you get this optimization problem. And you can do the same thing also for the constraints, and thereby it turns out that your original optimization problem, which looked like this here, turns into another problem with with different variables, but it's the same optimization problem. You can solve it in the same way. Right? So the logic that you have for this optimization problem also applies to this optimization problem. As a result, you have the z values, and for a particular x, so your training samples, you can calculate the u by simply multiplying your x with the different z values that you have. Right? You calculate these inner products in order to calculate your u vectors. And the advantage is that you can do this also with new vectors. Yeah. So here's a sample application where there's a whole movie of a face making grimaces and some mimic expressions and rotating, etc. And if you do sort of a linear projection, because it's a linear method, of the image into the two-dimensional space, you get this result here, and you see how face images that are similar group together. So the similarity is sort of preserved. So here are the faces that make sort of facial expressions, grimaces, and here it's all smiling. And this path here is sort of one small section of the video which has continuously sort of successes. This stretch of the movie is illustrated here. So it's seems to be a reasonable embedding. Okay, so there's a nonlinear version of that, and that's very simple, a very common trick. You simply expand your data space in a nonlinear way. So you do nonlinear expansion, which helps you to get from this original n-dimensional space into much higher p-dimensional space by some arbitrary fixed nonlinearities, so which is f of x here, and then you can do the same. Rather than with x, you would use f of x, but otherwise the whole machinery goes through as above. But the whole point is that Z now becomes much higher dimensional, yeah, because there are many more f of x's than there, or f of x components than there are x components.